In this video lecture, let us look into the detailed explanation for nanomaterial synthesis by laser ablation. What is laser ablation? Laser ablation is a nanomaterial synthesis technique where a high energy laser beam strikes this solid target. The laser removes atoms from the target surface and these atoms cool and condense to form nanoparticles. It is widely used to produce metal nanoparticles, carbon nanoparticles, carbon nanotubes, and quantum dots. Parts of a laser ablation: quartz tube, a heat resistant transparent tube, provides a controlled reaction environment for laser ablation and nanoparticle formation, allows uniform heating and prevents contamination. Furnace or heating zone: it surrounds the quartz tube to maintain high temperature during nanomaterial synthesis, prevents rapid cooling of ablated atoms, and promotes the growth of carbon nanotubes, nanowires, and uniform nanoparticles. High power laser provides pulsed or continuous high energy beam. Common lasers used include neodymium doped with yttrium aluminum garnet and excimer lasers. Target material: a solid block, can be metal, carbon, or semiconductor. Material choice determines the type of nanoparticles formed. Rotating target holder is optional. Slowly rotates the target during laser irradiation, prevents overheating or deep drilling of the target, and ensures uniform ablation and consistent nanoparticle formation. Substrate collector collects the nanoparticles formed from the plume, used for creating nanothin films or coatings. Gas inlet allows controlled entry of inert gas, example argon or helium, carries the ablated plume downstream, helps control particle size, cooling rate, and uniformity. Gas outlet removes excess gases and reaction byproducts, maintains a stable gas flow and pressure inside the quartz tube. Gas outlet ensures smooth movement of nanoparticles toward the collector. Vacuum or inert gas chamber: the entire setup is enclosed in a chamber operated under vacuum or filled with argon or helium. Controls the pressure, cooling rate, and nanoparticle size. Working principle: a solid target material is kept inside a vacuum chamber or inert gas atmosphere. A powerful pulsed laser beam is focused on the target surface. The laser energy heats the surface rapidly. The material melts, vaporizes, and ejects atoms called plasma plume. These atoms move away from the target and cool down in the surrounding gas. As they cool, they condense into nano-sized particles, 1 to 100 nanometer size. These nanoparticles are collected on a substrate, are allowed to cool to form a nanoparticle cloud in the chamber. The simplest key point for the working principle includes: the laser hits the target material and the material evaporates, cools, atoms cool in the cooled collector, and nanoparticles form. Laser ablation can be used to produce both single-walled carbon nanotubes and multi-walled carbon nanotubes. Single-wall carbon nanotubes can be formed with or without catalyst, but using metal catalysts such as cobalt, nickel, or iron greatly increases the quality and quantity of nanotubes. Catalyst-free methods work, but the yield is usually lower. Multi-walled carbon nanotubes can also be made by laser ablation, and they generally require a catalyst for good growth. The size and distribution of the catalyst particles play an important role in determining the type of carbon nanotube formed. Advantages of laser ablation: produces high purity nanoparticles, gives uniform size, especially for metal nanoparticles, good for toxic or high melting materials that are hard to process. Nanoparticles have clean, surfactant free surfaces, ideal for research. Thank you for watching this video lecture.